Hello and hi everyone. So today we are from section 3 are going to present our group assignment titled Second Order Differential Equations for the code subject SSCP2613 Mathematical Physics. These are our group members. From left we have Aisyah Dalila binti Abdul Aziz. In the middle we have Azwani Nadira binti Zamri, and at the right we have Muhammad Daniel Fitri bin Mizi. These are our contents for our presentation. First, we have derivation of solution to the second ODE. Second, we have question and stimulation of displacement against time graph. Third, we have discussion, and last but not least, we have references. So, without wasting our time, let us talk about our derivation of undamped. For the general solution to ODE, we have xt equals to a cos omega nt plus b sin omega nt, which is A and B are constant determined by initial conditions. The damping ratio for the undamped is equal to 0. Omega n is natural frequency of the suspension system, which is equals to square root k over m. So next, we're going to move to the derivation of underdamped. The damping ratio for underdamped must be between 0 and 1. The general solution, we have xt equals to exponential to the power of negative zeta omega nt a cos omega dt plus b sin omega dt, which is omega d is equal to omega n square root plus 1 minus zeta square, which is the damped natural frequency. Next, we move to the derivation of overdamped. The damping ratio for overdamped must be greater than 1, and the general solution is xt equal to c1 exponential to the power of negative zeta omega n plus omega n square root zeta square minus 1t plus c2 exponential to the power of negative zeta omega n minus omega n square root zeta square minus 1t, which is c1 and c2 are constant determined by the initial conditions. And last, we have the derivation of critically damped. For the critically damped, the damping ratio must be equal to 1. And the general solution that we get is xt equal to a plus bt exponential negative omega nt, which is a and b is a constant determined by the initial conditions.
Next, before we further ado, let's read the question. A 3.5 kg mass is attached to a horizontal spring on a frictionless surface. When a 12 Newton force is applied, the spring is displaced from its equilibrium position to 3 meters. Determine position of mass as a function of time after release. If mass initially released from rest, 1 meter to the right of equilibrium position. For first, we see at undamped. Undamped is an oscillating having constant or increasing amplitude. Firstly, we're using the Hooke's law for getting the key constant, which is equal to 4, and then we substitute into the equation 3.5x squared plus x plus 8 over 7 x equal to 0, and then we get the roots, which is plus minus 4 over 7i, and then we substitute into a cos 4 over 7t plus b sin 4 over 7t, and then we differentiate t equal to 0, we just at the end we get xt equal to cos 4 over 7t, and then we get the graph like this, position versus time. Second, we can look at underdamped. Underdamped is the condition in which damping of oscillator cause is to return to equilibrium with the amplitude gradually decreasing to 0. Firstly, we find the roots for the complex roots, which we use the roots function negative 1 plus minus square root 1 squared minus 4 over 7 squared, and then we get the negative 7 over 4 plus minus square root 15 over 4i, and then we get the complex root alpha and beta like this, and then we substitute into the equation xt equal to exponent negative 7 over 4 bracket a cos 15 square root 15 over 4t plus b sin square root 15 over 4t, and then we get the position versus time graph like this.
Next will be overdamped oscillations. The condition in which damping of an oscillator causes it to return to equilibrium without oscillating. Here is overdamped graph looks like, and also the solutions for overdamped oscillation. Next will be critically damped. The condition in which the damping of an oscillator causes it to return as quickly as possible to its equilibrium positions without oscillating back and forth about these positions. Up here also, the critical damp graph looks like, and also the solutions of critically damped oscillations. Next, we move on to discussions. To discuss the dynamic of the mass spring system under different damping conditions, we first need to understand the characteristic of each scenario. We'll base on our discussion on the given problem and the derived solutions. For undamped oscillations, the system oscillates indefinitely with a constant amplitude since no energy is lost to friction of air resistance. The frequency of oscillation is determined by the natural frequency, omega naught, which depends on the mass of the spring constant, and the initial displacement of 1 meter serve as the amplitude of the motions. For undamped oscillations, the system exhibits oscillatory motions with a gradually decreasing amplitude. The frequency of oscillation, omega d, is slightly less than the natural frequency, omega naught, due to the damping. Over time, the mass comes to the rest at the equilibrium position as the energy dissipates. Critically damped oscillations. The system does not oscillate but returns to equilibrium in the shortest possible time. The motion is a combination of exponential decay and a linear term. This type of damping is ideal for applications and requiring quick stabilization without overshooting, such as in automotive shops observers. And overdamped oscillations. The system does not oscillate but returns to equilibrium more slowly compared to the critically damped case. Both terms in a solutions represent exponential decays with different rates. Overdamped systems are used in scenarios where overshooting must be avoided, even if it means a slower returns to equilibrium. So, each damping scenario offers distinct behavior suitable for the different applications. The undamped system showcases pure oscillatory motions ideal for theoretical studies of harmonic motions. By understanding this behavior and solutions, engineers and scientists can design systems with desired dynamic responses, optimizing performance and stability based on the damping characteristics required for specific applications. Here are some references. And that's all from us. Thank you.